Welcome back to another video, and in this video, since we've only been talking about derivatives for a really long while now, and the thing is, we're not done yet, and so far we've only been talking about what we call explicit differentiation, right? So that's the differentiation where, it's like really easy to figure out, so it's like y equals mx plus b, right? We're just taking the derivative of that. But now we're going into like a different zone, right? So we have something called implicit differentiation. But before we even start discussing about implicit differentiation, we need to talk about the notation, right? So in the previous video, well, in the previous like few videos that I've been talking about, we've mentioned about this dy over dx. But what does this really mean though, right? It's the whole entire point of this whole entire thing is just it's the derivative with respect to x, right? Now, this x here, why do we make it to the respect of x, right? Why do we respect to x? Now, the whole point is that the x is in the denominator here, so this is why we make it respect to x. So let's say if it was dt over dw, right? Yes, this would be the derivative with respect to w, right? So now, this notation is a little bit confusing, but when we use it in implicit differentiation, it makes a lot more sense there, right? So we have to clear up some like assumptions first, right? So let's say we want to take the derivative of this. We want to take the derivative of 12x cubed plus 2, right? We put a y equals in the front, right? So now we want to take the derivative of the whole entire function here, right? But the thing is, we have a y in the front, right? So now this is what we mean by how this works. So when we take the derivative of this whole entire equation, right? On our right hand side, we have x. So we're gonna be doing the derivative with respect to x. So now the beginning becomes dy over dx and equals to 36x squared, right? That's how it makes sense. So the whole point was that we took the derivative of y with respect to the x value, the x variable here, right? In the beginning, of course, it's not going to make that much sense, right? But later on, it's going to make a lot more sense once we like expand it, right? Now, why does this actually work though? Right? Why does this actually work? So the whole reason behind it, right, is that let's write this equation again. Y equals 12x cubed plus 2, right? Let's say you're taking the derivative of y, right? That's just 1, right? So this is the whole point. So we added d over dx in the beginning because d over dx just means derivative right off the bat. It just means derivative. So d over dx of y equals the derivative of 12x cubed plus the derivative of 2, right? So now, let's see, right? So, since we're taking the derivative of y in this case, right? And x is in our little denominator here, we can just write dy over dx. And of course, multiply that by 1. Because the derivative of any constant, derivative of any variable is just 1, right? And then this would be equal to dx over dx of 36x squared plus dx over dx of 0. Now, the reason why we wrote dx over dx in this case, in this area, right, is because the variable that we're taking the derivative of is just x. So now we're taking the derivative of x in respect to x, right? And that would be equals to dx over dx. Now, dx over dx is just 1. So we can just cross that out here. Put it to 1. Over here as well. Put it to 1. And this whole entire thing is just 0, right? That's how it makes sense there, right? Now, of course, this didn't make sense to me when I started learning it, but the more practice problems that I did, it came to realization to me that, okay, so this is actually how we're supposed to do it, right? Some teachers, they just tell you to do, oh, y prime, right? They just tell you to do like w prime, right? I don't do those things because it gets a little bit confusing when you're looking at it. I like to write it in full fraction mode because the dy over dx, the dt over dw, right? It just looks larger to look at and it pops more, right? So now this brings us to implicit differentiation, right? So let's try this example first before we move on. Find dA over dt for a equals pi r squared. Pause the video here and see if you can figure this out. Now, hopefully you just took a look at it, and you're wondering to me, I don't see any t though, right? I don't see t, I only see r and a, right? So this is the point that we have here. So the way how we would do this is we would take the derivative respect to t, right, of a equals to pi r squared and take the derivative of that, well, d over dt of pi r squared, right? And in this case, since a here is by itself, we can just write dA over dt is equal to, now this is where it gets a little bit complicated here, right? So we're going to take the derivative of pi r squared, right? Stay with me here. We're going to take the derivative of pi r squared. That is just 2 pi r because of the power rule, right? And now, since we just took the derivative of r, we have to put this r next to this d here on the numerator. So it becomes dr over dt. Now, this is something that we also call related rates. Now, it's basically what you find as like the derivative when you're taking account of time, right? So now that was like a little introductory to what we do in implicit differentiation, right? So the whole entire point that we just did that, right, is because we wanted to set it in respect to something, and also we want to set it so that you don't have to like figure everything out before you put it all together, right? So you do it by section here. The whole entire first point that I did was on the left side of the equation, and then I moved on to the right side of the equation, and I figured everything out little by little, okay? So now, what if, just for whatever reason, right, what if the example was 2y cubed equals 4x to the fifth plus 9x to the second power? Now, you would tell me, hey, why don't we just move 2y, well, why don't we just isolate it and make it to y, right? That's gonna be a lot harder. right? If we isolate y, then we're gonna have a cube root somewhere, and we're gonna have to use chain rule when we're doing the derivative, right? And no one really wants that in the first place. So let's try using implicit differentiation to make this process a whole lot easier, right? So pause the video here, see if you can try to figure this out even, right? You might get it wrong the first time, but don't get discouraged because once you practice more, you're gonna understand it more. All right, so hopefully you just looked at this question and tried it out, right? We're gonna try doing this now. So what we're trying to find here is dy over dx, right? So that is our main objective for today. Find dy over dx. So let's take the derivative of 2y cubed equals that to the derivative of 4x to the fifth plus the derivative of 9x squared, right? So now we're taking a look here. Since we're going to take the derivative of y, right, we're going to have to set it to dy over dx, right? And now the derivative of 2y cubed is just 6y squared. So we're going to put the 6y squared next to it. Equals to the derivative of 4x to the fifth is just 20x to the fourth power. But don't forget, we have to put the dx over dx, right? The derivative that we just did was for the variable x, and also we're still doing it in respect to x. So it becomes dx over dx. Now, the same thing occurs with the second term here. It becomes 18x dx over dx. Now, one thing that we could do is this dx over dx, hey, let's just say that that's equal to 1, right? Because, of course, it is equal to 1. Dx over dx, the numerator and the denominator is the same, so equals to 1. So now this is the issue that we're having here. We're trying to find dy over dx. But in the beginning, we can't leave this like this, right? We have to isolate the dy over dx. So in this case, what I would do is I would divide the 6y squared to get dy over dx. So that means that dy over dx is just equal to 20x to the fourth plus 18x over 6y squared. And that is our answer. Believe it or not, that's how we deal with implicit differentiation. Remember, you always have to get this to be isolated to whatever you're trying to find, right? So it could be like 6 dy dx. You still have to divide the 6, right? So let's try a harder example here, right? And this harder example is this. Find dy over dx for x cubed plus y cubed equals to 6x plus 2y squared. Pause the video here and try it out. Remember, it's the same thing as what we just did in the previous problem, just a little bit more complicated because you have more terms here. Alright, so hopefully you just pause the video here and took a moment and see if you can figure this out, right? Now, let's start to solve it. So, we all know, hey, we gotta take the derivative of each of these terms, right? So our first term is x cubed. Now, the derivative of x cubed is just 3x squared. So we're gonna write dx squared down here. Now remember, you have to put the dx over dx. Make that into a habit. Now plus the derivative of y cubed. That is just 3y squared. Now remember, this time it's going to be dy over dx because we just took the derivative of y instead of x. Now we're going to put our equal sign here because we have one in the middle. the derivative of 6x, that's just 6. So 6 dx over dx, because we took the derivative of x here. And now the last term that we have is 2y squared. And the derivative of 2y squared is just 4y. Now remember to put a dy over dx. Alright, so we're trying to find dy over dx here. Now, let's clean this equation up a little bit. So this gets crossed out to 1, and this also gets crossed out to 1. So what we have here is 3x squared plus 3y squared dy over dx equals to 6 plus 4y dy over dx. Now, how can we make it so that we can isolate dy over dx? Because that's what you're trying to find. Now, the way to do this is that we must move all the dy over dx terms on one side of the equation. In this case, I'm going to move it on the left side of the equation, right? So we're going to subtract the 4y dy over dx. And of course, we're going to subtract the 3x squared here, just so we can move it onto this side, the right side of the equation. So minus 3x squared. Now, we see a common factor here. And the common factor here is just dy over dx, right? So we can factor that out. It becomes dy over dx times 3y squared minus 4y equals to 6 minus 3x squared. And now we can just divide it just to isolate the dy over dx, and that'll be equal to 6 minus 3x squared all the way over 3y squared minus 4y. And that is our answer for this implicit differentiation. Now, just to recap on everything, right? Implicit differentiation, we use it whenever we have these variables that are stuck together, right? So in this case, even if we try to reorder these terms up here, right, to make it so that y is on one side and the x is on the other side, right, it wouldn't really match. It wouldn't really work out that easily because there's a lot of things going on here, right? So this is why we do something called implicit differentiation. And we have some more examples that we can do here. So we're going to do this one last example here, and hopefully it's enough for that we all understand we're on the same page here. So let's try this example here. Find dy over dx for 2y squared equals 4x plus x cubed minus 1900. Okay, take a moment here and pause the video. See if you can try to figure this out. This one shouldn't be that hard because it's a lot easier than the previous one that we did. The previous one that we did was really, really hard. It was really complex. So, see if you can figure this out. Alright, hopefully you just took a look at this problem and tried to figure this out. So now let's try to solve it. Now our first term here is 2y squared. Now the derivative of 2y squared is just 4y, right? So we're going to write the 4y here. And we took the derivative of y in respect to x, so we're going to write dy over dx. That is going to be equal to the derivative of 4x. That's just 4. So 4 times dx over dx, because our variable was x, plus the derivative of x cubed, which is 3x squared, dx over dx. And lastly, the derivative of 1900, which is just equal to 0, so we can knock that out of the ballpark here. Now, we can simplify this equation a little bit more, right? So this dx, gone. This other dx is also gone, right? So now, once we rewrite this equation, it'll look like this. 4y dy over dx is equal to 4 plus 3x squared. And in this case, right, we want to find what is dy over dx, right? So now we're gonna divide 4y so that we can isolate the dy over dx. And your final answer comes out to 4 plus 3x squared over 4y. Now this problem was a lot simpler than the last one that we just did. The last one, it required a little bit more of thinking, right? So as a recap of everything that we've taught in this video, we've said that the derivatives that we were doing before were just explicit differentiation. Now we've approached into the implicit differentiation world and also touched upon of related rates. Now related rates is going to be a whole different topic because it talks about how things are changing in respect to time, right? So just for this video, we're only going to be talking about implicit differentiation. So hopefully you understand a lot today, and make sure that you guys keep on practicing these problems, and I'll see you guys in the next video.